Hi, welcome to Embracing Single-Stride 3D Object Detector with Sparse Transformers. In recent years, in the field of autonomous driving, 3D LiDAR-based object detectors typically first project the point clouds into bird's-eye view images, then use the object detector with very similar architectures of 2D detectors, such as using similar detection head, using similar label assignment strategies, and using similar multi-strap backbones, or sometimes IPN-style backbones. But there is one key observation which is largely overlooked by recent works. That is, in the world of 3D, the scale variations are much more limited. Here in this figure, we can compare the object sizes of a COCO dataset with an on Waymo dataset. We see from the histogram that on COCO dataset, we can observe a strong long tail phenomenon in the distribution of object sizes, but no long tail phenomenon on Waymo dataset. Second, we can also observe the object sizes on Waymo dataset tend to be much smaller as object sizes on COCO dataset. From the perspective of architecture design, we know multi-thread architectures are very good tools when dealing with large-scale variations. So this leads us to think, do we really need downsampling in 3D object detectors? To answer this, we carry out a simple pilot study. We use point pillars as a baseline and gradually remove all of its downsampling layers. After removing 2 downsampling layers in point pillar, we see a performance improvements in all categories. But there are 2 important problems we need to address if we want to design a successful single-thread architecture. First, the shrinkage of a receptive field due to no downsampling. Second, the increase of computational overhead due to a much higher resolution feature maps. To address these problems inspired by swing transformer, we propose the design of a sparse regional attention. We divide the bird's eye view images into non-overlapping fixed size windows. Each window can have a size of around 3 meters to 6 meters, which is the hyperparameter. Inside each window, each valid voxels or pillars can act as a query or key, or in other words, tokens, and are fed to a transformer block. To account for objects that are truncated by the boundary of the windows, we apply window shifting after each transformer block. The sparse regional attention design have 2 key advantages. First, even with single-thread architecture, we can still achieve large and flexible receptive field. Second, due to the sparsity of point clouds, for different windows, the number of valid tokens will be different. And the design of a transformer was a very powerful tool when dealing with variable length input. So we replace all the convolutional layers in point pillars and achieve a very simple single-thread design. We compare our single-thread design with state-of-art methods on Waymo dataset. We see our simple design achieve a very strong performance, and especially on pedestrian categories, where our methods outperform state-of-art by 3 to 6 MAP on level 2 split. To understand if our single-thread architecture have enough receptive field for large vehicles, we report the breakdown metrics for objects with different sizes. And when compared with vanilla convolutional-based or sparse convolutional-based single-thread architectures, our design have better performance with fewer parameters and with comparable computational cost. And for more extensive results, please refer to our papers. So finally, for summary, given the key observation that there is much more limited scale variations in the world of 3D, we present a clean single-thread architecture and achieve strong performance. And there is still a large room for further improvements. Please stay tuned. Thanks for your time and interest.